let's explore Lie group transformations. At its core, a Lie group is a fascinating mathematical concept that marries two fundamental structures: groups and smooth manifolds. First, let's recap what a group is. A group is a set of elements, along with an operation, that satisfy four key properties: closure, associativity, the existence of an identity element, and the existence of inverse elements. Now, a smooth manifold, on the other hand, is a space that locally looks like Euclidean space. Think of the surface of a sphere. It's smooth, meaning we can do calculus on it. A Lie group is both a group and a smooth manifold, where the group operations are smooth. This smoothness of the group operations is what makes calculus applicable to groups, and is crucial. This means the group multiplication and inversion operations are smooth maps. Let's consider some crucial examples. First, let's consider the real numbers under addition. The group operation is simple addition. The identity is 0, and the operation is closed. The inverse of any element x is simply x. This whole setup forms a one-dimensional Lie group. Next, let's consider the circle group. The action is complex multiplication, and elements are on the unit circle. Then, we have the general linear group, nxn invertible matrices under matrix multiplication, and the special orthogonal group, 3 by 3 rotation matrices under matrix multiplication. So 3 is extremely useful in physics. Now, what's a Lie group transformation? It describes the action of a Lie group on a manifold. Formally, it's a smooth map from the Cartesian product of the group G and manifold M to M, which satisfies two properties. First, the identity element in G maps any element in M to itself. Second, group G's action preserves the group structure of M, or G acting on H acting on P, is the equivalent of G times H acting on P. For example, SO3 can act on 3D space by rotating vectors. Similarly, the real numbers can act on the plane or any Euclidean space through translation. These actions are smooth and respect the relevant group structures. Why are Lie groups and transformations so important? Well, above all, they are essential for describing symmetries in physics. Rotational symmetry, for example, is described by SO3. Translational symmetry uses the Lie group of real numbers. The laws of physics do not change under rotation or translation. Lorentz invariance, important for special relativity, is another example. And in quantum field theory, we have gauge symmetries. These symmetries relate to the fundamental forces and are also described by Lie groups, and more specifically, Lie group transformations. Finally, let's briefly consider the Lie algebra. Every Lie group has an associated Lie algebra. The Lie algebra can be viewed as, in some sense, the tangent space of the Lie group at its identity element. The Lie algebra captures the local structure of a Lie group. Its elements represent, in a sense, infinitesimal transformations. For example, the Lie algebra of SO3, denoted SO3, consists of 3 by 3 skew-symmetric matrices. These matrices correspond to infinitesimal rotations around the x, y, and z axes. The exponential map connects these infinitesimal transformations to the full rotation matrices. To summarize, Lie groups are groups that are also smooth manifolds. Lie group transformations describe how these Lie groups act on other manifolds. These actions help express symmetry, which is crucial in physics. And the corresponding Lie algebra associated with a Lie group can be viewed as its tangent space at the identity. Further questions are always welcome.